Wow. Yo. What's up, RustConf? This is going to be a less formal talk because I'm just naturally a less formal person. And it's also not going to be incredibly technical, but I think you guys are going to find it interesting. I find it really interesting. So you've probably read the brief. I'm here to tell you an adventure story of some crazy folks that were new to Rust attempting to build just like a critical piece of infrastructure for their company in it. And we'll see how it turned out. You probably already know the conclusion. So my name's Carter Schultz. I love building complex systems, and I also have the incredible privilege to work at this pretty dope company called AMP Robotics. Over the last 5 years, I've been helping AMP to achieve its mission of trying to make recycling fundamentally more efficient and economical. AMP's a startup, and it's been the startup wild ride that startups are, trying our hardest to just make recycling work. We've had some moderate success, like 5 billion objects were sorted by our systems last year, which, well, I'm really proud of it. That's really cool, but it's also just a tiny drop in the global waste stream. So there's still a really long way to go. So there are a lot of companies out there that are trying to make the world a better place. AMP isn't unique in that, but I feel incredibly fortunate to work at a company that's trying to make the world a better place in a way that's also economically viable. We believe that better technology that can make recycling cheaper than landfills even, will force companies to adopt recycling, and more will get recycled in the world. That's a good thing. This industry needs a shakeup. Recycling rates in the US have been stuck at just above 30% since the early 2000s. Something has to come in and kind of kick this industry in the pants, change the way that recycling is happening to really stand a shot of making a meaningful difference. And this is a really important problem for humanity as a whole to solve. The value of the raw materials that our society burns or throws away just boggles the mind. And most of these materials are thrown away not because they can't be recycled, not because no one finds value in these materials, but because it's deemed too hard to efficiently get these materials to the places and the people who can make good use of them. Producing goods from recycled materials has a dramatically lower carbon footprint than using virgin materials, and if with somehow technology can make it cheaper to recycling, we have the chance to save humanity as a whole, not only just billions of dollars of value that we're throwing away, but offset gigatons of CO2 that is being released from industrial processes. Now, if you look at the recycling industry overall, there are a lot of problems with it. We could spend this entire talk with me just ranting about the problems in the recycling industry, but at least for now, AMP is tackling just one facet of that, and that's the sortation problem. So I introduce to you our opponent. We are in a war against distribution centers. If you've seen Amazon's videos of their incredibly sophisticated distribution centers with robots scurrying everywhere, what are those robots doing? They're taking neat, sorted, orderly pallets of goods and mixing them up as much as possible, as efficiently as possible. Their job is to increase the entropy in these systems. And the perfect recycling sorting facility would do everything these distribution centers are doing, but backwards, just as efficiently. Taking all of these commingled goods and getting them sorted out into as many distinct types and purity of materials as possible so they can go back to where they can best be used. So I said the word earlier, entropy, how chaotic things are. That's the fundamental law of physics that makes sortation a hard problem. The entire supply chain of what it means to make a good for society involves taking raw materials, mixing those raw materials together, commingling those raw materials as products in consumers' hands, and then somehow if we want to recycle, we have to reverse that entire process back to those virgin raw materials in a good way. So I'm calling out Amazon here a little bit as our opponent, but really what I'm trying to say with this slide is that so far humanity has invested literally billions of dollars in making the front half of this pipeline as efficient as possible, while largely ignoring the back half. There is massive room for improvement in the recycling industry, but it's not sexy, it's not easy, it's not clean, it's not fun, and so people aren't tackling it as strongly. And that's kind of where AMP comes in, and this is all just company preamble to tell you why we're doing the things that we're doing. So a lot of you have probably seen this graph before or versions of it. AMP exists because we are riding on the coattails of the machine learning revolution. Machine learning models by like publication date have been growing super exponentially in recent years. That is on a y-axis log scale. So we crossed millions of parameters in models in the early 2000s, and it only took us until 2014-ish to cross billions of parameters, and that's kind of where AMP got founded. This exponential growth in AI model capabilities has been fueled by the exponential growth in compute capability provided by GPUs. Now, a lot of people say, and I've said it myself, Moore's law is dead. Yeah, maybe by some definition, but from where I'm sitting in practical purposes, while CPUs have bottlenecked, GPUs have more than made up for that performance gap and have allowed incredible compute to exist at the edge, unlocking fundamentally new technologies. So you want to make recycling better, you want to make sortation in recycling better, AI revolution's happening. What do? You make a neural net that can identify recycling. When our founder kind of went after this and said he was going to do this, a lot of people told him it was impossible because 5 or 6 years ago, this really did seem impossible. The idea that a low-cost RGB camera and a low-cost off-the-shelf graphics card could successfully identify recycling materials to sufficient levels to make the system work was a big question. Turns out we were right, and we have now a neural network that can identify more materials than any previous solution, is lower cost than any previous solution, and very quickly in its development exceeded the accuracy of human sorters, meaning this neural net is better than you are at telling what category a recycling material belongs in. So that more than met kind of sufficiency in the marketplace. Now, the world's best neural network doesn't just magically solve the problem. You have to do something with that neural network to achieve some real-world changes. And what AMP started off with was coupling this neural network with an off-the-shelf commercial pick-and-place robot to do the sortation itself. I've spent most of the last 5 years writing the C++ code that runs on these embedded systems to integrate these robots and cameras together and run these neural networks at speed to efficiently make robots reliably sort in recycling facilities around the world, which is, it's hard. I'm giving you that context so you know I come from a C++ background and I've been building hard stuff and I have regrets. This is kind of the cool money shot. This is what I love to show. These are our robot systems. I've had the privilege of watching these robots do millions of picks in a month in hundreds of facilities around the world, day after day after day, sorting recycling in a more efficient way that was previously possible. So like, yay, you're done, right? We don't have to do anything past that, right? Well, no, we decided that wasn't good enough. While these robots are fundamentally more efficient than the technology that exists before, it's not achieved our mission yet, guys. Like, the world is still struggling with recycling, so what comes next? And you've seen the title of the talk, so you know the answer to this rhetorical question, but AMP imagined, what if instead of building technology that retrofitted into existing recycling facilities, what if we built a recycling facility from the ground up around this neural network technology? What if for the first time you put a camera on every single conveyor belt in a recycling facility so you knew exactly what material was where at every point in the facility? That could be really cool. That could work. Wouldn't that be nice? And so we did it. We tried it. We said we would go out and actually try to build that thing. And this is a very kind of classic startup story. Like, the CEO walks into the room one day and the director of engineering walks in one day and they kind of gather the team together and tell us kind of bit by bit quite how this is going to go. And they say, okay, let's go build it. We're going to build the recycling facility of the future. It's going to do all of the things that we could dream. We are going to invest our time and our resources making as good of a thing as we can possibly build. And there's me in the corner, all starry-eyed and happy and like, yay, we're going to do it. Well, then the first thing that they added to that pile is it's going to be a pretty big facility. It's going to try to process 20,000 pounds of recycling an hour. That's a semi-truck coming and leaving the facility every 2 hours. That might sound like a lot in the grand scheme of these recycling facilities. That's actually a pretty small one, but it was more than intimidating enough at the time. And it means that, say, if you're the guy writing the control system for it and there's a little hiccup, it's really easy to make a 500-pound mountain of trash in the facility somewhere, and you better go grab a shovel and start digging out the equipment. So that was scary. The next kicker was, oh, we're a crazy startup, so immediately we're going to go into 24/7 operation on this thing. It was critical for us to figure out as soon as possible if this whole thing was going to work out or not. So we wanted to tax the crap out of this system right away. Oh, and it's going to be built in another state, so you're going to be remotely supporting it. So the reliability requirements they were asking for was also insane. So by this time, I'm sweating it. I'm feeling it like, okay, this is going to be a doozy. This one's going to be a challenge. Oh, one more thing. From the day they told us about the project, they asked the facility to start running in 6 months. If you don't know you can imagine what it takes to build a factory. That's fast. That's crazy fast. That's dumb fast. But whatever, boss says jump, I say how high. So we dove into it, but one kind of extra mitigating factor, we're doing this in the middle of a pandemic and the worst global supply chain crisis ever. So like right off the bat, this just seemed impossible. It seemed like there is no way that we could pull this off. Great. AMP had a lot of the building blocks for putting this factory together already. We had previously built a really small scale facility in Denver right next to our headquarters so that we could run experiments and figure out like, could this thing work at all? And we'd gotten some good results from that. But one of the biggest things that we thought was going to be a problem when we try to scale this facility up was the facility control system. We need a central controller that's going to be responsible for integrating all of the equipment in the facility together, telling it when to run, when to stop, how it's going to work. And we'd done that in our small scale facility with a little tiny Python monolith. And it had worked. Like we could run a facility off of it, but it was obviously already showing its cracks and showing like, hey, this thing's not going to scale much bigger, and we were about to build a much bigger facility. So I got made responsible. Hey, make a facility control system. If you're a good engineer, which I claim to be, but probably am not, if you're ever asked to build something, your first question should be, hey, can I go buy that thing instead? Like, please, is there an off-the-shelf solution? And we frankly went shopping for one. We went around to multiple vendors and said, hey, please build this for us. And they were like, yeah, sure, we can do this. We'd love to be a partner with you. And then I said, yeah, and the facility's going to start up in 6 months. And they laughed me out of the room and said, no way. Hell no. Like they were like, we could start looking at your project about 2 years from now. If you guys can wait till then, right? So our hand was kind of forced. We had to build the control system ourselves. We had to integrate it ourselves. And that was really scary, but we dove in on it. So the team that was involved in building this whole thing was me. At this point, I have about 6 years of experience building some pretty crazy systems in C++. I felt really comfortable there, and I dabbled in Rust a little bit. I had a couple juniors that were pretty fresh to the company working with me. They were mostly C++ background. All of us knew a little bit of Python on the side too. One other person had dabbled in Rust. The point here is that none of us knew Rust. And so, like all people who don't know Rust, we weren't sure yet if anything was going to be possible for us. Sorry, I got these slides out of order. I stumbled over it. We're going to take a pass at this again. We were looking at the tools that we had available to us. We knew C++, we knew Python, and we were pretty dang sure neither of them were going to work for this. If we tried to build it in C++, our developer velocity was going to be way too slow. I knew how complicated this system was going to be. I knew what it took to build systems like this, and it definitely wasn't going to get done in time, and it was definitely going to be full of bugs. We also were like, hey, well, we could definitely get it written in time in Python, but would it work? Would it actually run? And one of the biggest challenges in doing a facility control system like this is the first time that our system was ever going to see full load was on the day the facility tried to start up. Like, we literally couldn't turn all the electrical components on to test them in our lab before the facility started up. So we could try like mock tests and stuff, but the first time we're actually going to do full integration testing with all the hardware components, the CEO is going to be standing over my shoulder looking at a stopwatch going, when's the facility starting up now? So scary, 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 scary. And we came to the conclusion that a lot of people come to, screw it, let's write it from scratch in Rust. We don't know it, but we'd been hearing in the background the siren call of Rust, these promises that the Rust community has been putting out in the world. You can have your cake and eat it too. Every concern and problem that we were scared about on this project, Rust seemed to have a magical answer for. So, we said, YOLO, let's try it. We're gonna learn Rust, we're going to hire more developers, we're going to teach them Rust, bootstrap Rust development inside our company, and just go for it. And it's hard to really convey like emotion in the past, but this was an agonizing decision for me at the time. I asked everyone I know, am I crazy? Am I a fool for trying this like weird crab thing? Does it make sense or not? But the promises that the Rust community were making so aligned to the challenges I'd seen in my previous tools that it was, damn it, give it a try. And, a big factor that drove this decision was, honestly, I didn't think it was going to be possible if I didn't try Rust. Like, nothing I had lying around sitting on the shelf was going to solve this problem, so might as well try something new. Before I get into telling you the sins that we committed in Rust, I think it's very important to caveat the fact that we did not touch the fundamental safety of the factory. There are very traditional ways that kind of base safety is achieved in factory settings with safety-rated hardware that is redundantly wired together. We used all of that. So below the insanity of our Rust control system that's doing the high-level control of the facility, we could be extremely confident that if anything goes wrong, there's a big red stop button everywhere, and those buttons work, and we can't screw them up no matter how bad of code we write. So Rust is good, but we're not crazy, and we did not touch safety with it. So the director of engineering at my company strongly suggested I put this slide in after he saw this talk. So this slide's really trying to give you guys a sense of the devices that we're integrating against. This is, in factory sense, not a huge one, but there's still a lot going on in here. We had 2 massive vendor-provided systems that had PLCs and logic controllers of their own that we needed to integrate with. We had about 30 of our own AI systems that we had to integrate against our own APIs, and I gotta curse myself for writing a terrible API to integrate against. And then a lot of this is conveyor belts. The reality is most of what a recycling facility is just conveyor belts. Those conveyor belts have motors. Those motors have motor controllers that are big industrial pieces of equipment that drive it, and that was a ton of it. And then there's just I/O everywhere in the facility. So we had a bunch of components to integrate against that all spoke just a gross mishmash of different industrial protocols, and at the end of the day, this facility is drawing about 1 megawatt of power. Just to kind of, I can't show you guys a lot of photos of it, but here is one of the 3 electrical control cabinets that runs this facility. So this cabinet's doing like 1/4 of a megawatt. It's just big electronics, big thick power cables. It's scary stuff. So we have to integrate against all of these devices, but what functionality is actually needed to make this facility run? It's not a lot. Well, no, sorry. It's a lot. It's a lot of things. None of them are that hard. The reality is, like, building a factory control system, a facility control system, it's not rocket science. It's just an enormous amount of software plumbing. There's a lot of little tiny features that you need to be able to operate the facility day to day. None of them are very hard. There's just so gosh darn many of them. And then the real challenge for us was like, hey, this facility is going to be 24/7 in a different state. I don't want to get called at 3 a.m. So it's got to be not only reliable, but it's got to be observable. We got to have good data. We got to have good logging. That data's got to be making it to the cloud. If I haven't said it yet, this is all running on the edge. We're building a server farm in the facility. So we ended up building a lot of UIs for this. Those UIs ended up being Angular UIs. Those are kind of scattered throughout the facility on touch screens, and all of this has to communicate together and get back together. It is just a lot. One of my first rules of robotics, or first rule of building complex systems in general, is simplify the problem. Up front, when given a really, really hard task, do everything you can to remove as much of the difficulties from it. One of the biggest ways that we did that when building our factory control system is we forced everything to be Ethernet. If you go into the industrial automation space, you will find a bunch of different protocols from a bunch of different vendors with big piles of marketing telling you why they're more reliable and why they're more perfect and why they're more introspectable and why your facility won't go down if you use their stuff. But the reality is, like, $1,000 have been spent making Ethernet reliable for every dollar that's been spent on any one of those industrial protocols. Ethernet absolutely can run a facility, and by making the entire facility run on an Ethernet backbone, we play to Rust's strength. Rust knows how to do networking. Networking is really observable. We can run packet captures on the routers and see what's going on in our facility, and it meant that we had one physical layer to deal with, which simplified things a lot. On the flip side, we're pumping about 20 gigabits a second of data through this network that is mostly camera data coming from all of those cameras scattered out throughout the facility to the actual servers in the server rooms running this. And that means our motor control commands are going out on the same network that gigabits of camera data is coming back on. So a little bit of care is needed. You gotta do the math and balance it out. It took a while to get the network completely healthy, but once we did, simplified the project a lot for us. I had servers in quotes on the last slide because the servers that we ordered ended up being 9 months late. Not it took 9 months to get them, they arrived 9 months after the facility started up. So our pivot was a bunch of gaming PCs bought off Amazon. Hashtag Prime 2-day shipping, baby. So that might look like a server rack. That's a big pile of gaming PCs masquerading as a server. Most of these are actually running that C++ application that's doing our neural net stuff. One of these servers is being our central controller for the whole facility. That's pretty cool. I'm going to talk a little bit about like the architecture of what we built. The thesis of this talk, if you haven't caught on, isn't like, hey, here's how to build a facility control system the right way. It's an adventure story of some idiots building a facility control system. So don't copy this. If I was going to build it again, I wouldn't build it this way. But just parting the kimono on what we did build, we built the thing as a series of microservices. The right way to do this would have been actors and to use async, but we had a lot of baggage from our experience in C++. In C++, it's so easy for one code mistake to corrupt an entire process's memory, bring that entire process down, and if that takes down your whole facility, that absolutely sucks. So one of the tricks we brought over from our C++ programming days, running everything as its own process, so if any one chunk of code gives up and crashes, it only takes down that one part of the stack. And given the kind of latency and timing requirements we had, it's actually the case that like 90% of the nodes in the system can have a completely fatal crash, go down, restart, come back up, and the entire facility keeps trucking without a single hiccup or hitch, which just fundamental reliability kind of baked into the architecture. So that was really nice. Pretty proud that it all worked out at the end of the day. But what is the end of the day? We have dozens of processes running, talking to hundreds of devices, speaking a bunch of different protocols, sending thousands of messages a second over a message bus, built by noobs, controlling a huge pile of very powerful industrial equipment. So obviously this is going to go well, right? And it would be reasonable to come to the conclusion here that I'm up talking to you today to ask for donations to the Save AMP Fund because this pile of spaghetti we built burned down our factory. I'm not. I'm here to tell you that it went well. It went really well. It went way better than I possibly could have imagined to, and I feel guilty kind of being up here on this stage today. I feel like someone who won the lottery telling people, hey, go invest your life savings in lottery tickets. Trust me, guys, it works. But I just felt compelled to share this story with you. We built an incredibly complex system in a really short amount of time, and it just worked. It was like a miracle. No software just works. This one did. So I had to be that guy who stood up and said it. Hey guys, it's possible. You can roll lucky on. You can roll a nat 20 on your code quality check. So some just quick facts. I think these are fun to know. We had about 20 different types of the individual microservices running, about 100 microservices in total on this single gaming PC. I think the gaming PC was at like 12% CPU utilization handling it. There's a lot of things that we're talking to. None of it's that big of data and none of it's that high frequency, so it's not crazy. The total code size isn't that impressive. 54,000 lines of code from like 3 people in 6 months is a little crazy. Would not recommend doing that again, but it worked out. And it, like, just to allay people that are like, oh, Rust, long compile times, no, it's bullshit. Like, you can build very complex software and it will compile just fine for you guys. So, why am I here? Why am I standing up in front of you guys? I'm here to convince you Rust made this possible. I honestly and firmly believe my decision up front was right, and this project would have been impossible without Rust. I tried to sit down and do my real, honest estimates. I have built multiple systems in C++ that got to the 100,000 line of code complexity level. I have worked in C++ for a long time. I am a C++ expert up on this stage preaching to the choir and telling you that I think by using Rust, we built it in 1/3 of the time with half the developers and 1/10 the number of bugs. That's incredible. Like, I'm preaching to the choir. I know I am. But guys, this is game-changing. Like, real-world change is being made possible by just how much better Rust is. And so if you've ever been looking for, like, C++ expert says Rust is just better, cite me. I'm here. You can use me. And again, back to those promises that the Rust ecosystem made. They're true. Like, everybody in this room knows this true, but the world needs to hear these promises aren't just aspirations. They are lived, they are real, they are existing in it. And the biggest thing that I want to kind of give Rust credit for that I don't think it gives itself enough credit for is the quality of the package ecosystem out there. We used dozens of off-the-shelf packages. Those libraries were of exceptional quality by maintainers that were dedicated and responsive and helped us on it. The package ecosystem in Rust, we might take for granted if you're coming from JavaScript or Python. Coming from C++, it's like finding nirvana, guys. It's so good. And so all of the things that Rust does matters, and they contribute to a team being able to pick up this language, learn it quickly, integrate it into their stack and software, and build truly incredible software with it very, very quickly. So I'm running out of time. Takeaways. I'm an idiot. Our team are idiots. We don't know what we're doing, and yet somehow we managed to succeed, and I blame the Rust community for that. It's a miracle that this thing worked. It shouldn't have worked, and it did, and Rust made that possible. Rust is making it fundamentally possible to build more complex, more reliable, and larger scale systems than previously possible. And fundamentally, my internal benchmark for what it is possible to do with software has been reset. When teams are able to, in less time, with less resources, fundamentally build more valuable software, that changes the world. And so, parting shot for you guys, Rust is saving the world. Real-world change is happening as the result of all of the incredible effort that is being put into this ecosystem. Millions, if not billions, of objects of recycling are going to get sorted today because of what this community has built. And I just have to say thank you for that. Thank you, thank you, thank you. AMP's journey is far from complete. We're just at the beginning of learning how much value there is in the waste stream and whether these facilities work or not, but I can definitely say Rust is going to be a huge part of what we build going forward. Final thing, at the very beginning of this conference, Sage reminded us all to thank the Rust educators in our lives. So my parting shot is to blame John Jengset and his absolutely incredible YouTube content for convincing me that Rust was possible, convincing me that I should consider Rust, and guiding me on my Rust journey. So shout out, thank you to John, who none of this would have happened if it wasn't for your damn YouTube videos. But that's it, guys. That's the talk. It's not crazy. We just built something cool in Rust, and I wanted to share, so thank you all.